Okay, good morning, everyone. And I'm Shipeng from Ant Group, and this is our new benchmark. And we write a paper, and I'm happy to say that we received the best run-up paper in the EAB track in the VLDB 2025. And this is actually the collaboration, it's collaborative effort we finished by the FinBench working group. And uh, before I actually dive into the details of the benchmark, and I would like to give a brief background of the graph data, the graph models in Ant Group. Ant Groups, we have the product, maybe you have some heard before, that's Alipay. And the users can use Alipay to transfer monies. Six, uh, they can transfer monies there, and they can purchase some goods, and they can pay some credits, and apply for loans, and the users can have social events in the Alipay. So behind all these business units, we have all this data, and we model this data as graph, and we use a graph database to process and store this kind of data. And for the data scale, we have around 1 billion registered users in Alipay. And regarding the transaction count, we have around 100 billion transactions. For the actual graph size, we have looked in our business clusters, and the graph size ranging from the 10,000 to the 1 trillion. And but the next question is, when we want to find some benchmark to evaluate our database, and we take a look at the existing benchmarks for the graph database, like the SMB and Linkbench and the Graph Analytics, which most of them are from the existing LDBC works. And we found some features we identified in the financial scenarios is not included in this kind of benchmarks. Like we identify that we have the age multiplicity, which means there are multiple ages from the between the vertex pairs. And these are the data set characteristics. And the third red box here, we illustrate some the path finding and the temporal queries. These are the characteristics embedded in the financial queries. I will dive into the details later. So, following the traditional LDBC 12-point driven methodology, which means to balance between the real-world business complexity and the benchmark abstraction, we identify the choke point embedded in the dataset and the queries, which means it's the bottlenecks that the workload will challenge the systems, and it can guide our optimization on the systems. So we use this traditional LDBC 12-point driven methodology, and we take a profile the data set, and we take a look at the queries and the workloads, and we finally applied these characteristics to the entire framework. So first, maybe we take a look at the schema. We surveyed about around over 20 business clusters, and we use a typical transaction scenario as a design. So we actually have 5 vertex tabs and 9 edge tabs here. But in the financial data, we also observe that this kind of characteristics, like the entities are usually modeled as vertex in our system, and the edges are usually reference activities among the entities. And in a common property of these vertex and edges, the timestamps are usually frequently used. And we have various subtypes of semantics, which means in some businesses we usually have the account type 1, type B, and type C. Um, and we have the rich properties in our vertex and edges. And we have the edge multiplicity. You can see the solid arrows in the schema, which means like the accounts, they can transfer multiple monies to another account, right? So we also took a look at the data distribution. The polar distribution of the vertex degrees is a common distribution in the graph data. But actually, we sampled three subgraphs from the online production environment, and we do some profiling, and we found the difference between the financial graphs to the social networks is the social network usually the power distribution is limited by the maximum constraint of the social media platform, which Facebook, they limited the users can have at most 5,000 friends. So this kind of distribution in social network is actually a bounded skewness. But in a financial graph, we find the unbounded skewness, which means that you may get a higher degree of the harbor vertex in the financial graphs. And after we got the data model and the data distribution, we apply this configuration to our data generator. We implement scalable and configurable data generators, which simulates actual financial activities. And then we segment the overall data to two parts. The first part is snapshot data. Snapshot data for bank loading as basic data in the graph database. And the second part is the incremental data, which is designed for the following red query generation. And this is actually following the traditional, the LDBC benchmark framework, and we have the generator here to generate the factor tables. The factor tables is actually the statistics of the query footprints. A common sense here is the cost of the graph queries. It varies depends on the vertex you're starting from as a graph traversal. Yeah. So we use factor tables to guide the following read-write query parameter selection to ensure the benchmark reliability. And the following slides are some case studies of the typical queries in the financial benchmark. The first is the temporal query. The temporal query, this is a TCL4 in the transaction workload. The TCL4, it matches a transfer cycle within a specified window between a start time and an end time. And the feature of this kind of query is the query usually looks back in a limited time window. They filter the edges between the start time and the end time in traversal. The practice is we usually to do some code and hard data storage tiering, and we probably can deprecate some data with data compaction. And the true here is because the queries usually filter the edges by the time steps. So the queries they can benefit from the temporal access locality, especially on the edges. And the next typical query here is recursive path filtering. This query TCL1 is to match the transfer passes in the ascending order, temporal order. It's actually in business, it's tracing the divergence or the downstreams of the fund flow. And we usually giving a path there, and we usually to define the filters like we expect the order of the timestamp is ascending order, and we expect the amount order is descending order. And if we want to make it more strict, and we can add length of the timer window, which you can see the K here. K is a constraint, which means the next hop, the age is no more than like 5 hours or something like that. This is more strict filters here. So the features here is to the query match the path filled by the monotonic predicates. And the trial point here is the query you can benefit from the path level predicates pushing down, which means you can prune the invalidate intermediate result earlier, and it can save memory and improve the performance. And this is a redirect query, which actually the queries usually check the graph pattern indicating the illegal activities before we actually executing the right operations. For this query, you can see here is complex read transfer cycle detection. And when users they want to transfer money to somebody else, and we usually run some risk control strategies before we actually permit this kind of transfer. So the feature of this kind of query is the query is a complex read wrapped in transaction. We think about this query. You can if you can write this kind of query in a transaction, it will be easy to write these query patterns. If you don't have the transaction to support this query, you need to some like this age doesn't exist, and you need to write assuming this age existing here, and there's another loop from the desk to the source. So the choke point here is to the queries can benefit from the optimization on the query write operations contention the conflicts. If you look from the system side to take a look at this kind of query, the query is actually a simple write here and a complex read here, and the end of this loop is of this workflow is conditional write. So we can parallel executing this kind of query, and but you need to take care about the write operation contentions. And we have four query types in the transaction workload. And the write queries and the redirect queries are the incremental data generated from the incremental data. And the read queries are mixed as random walks on the graph, which following the traditional LDBC style. And it's like the simple reads, the input of the simple reads are the output of the previous complex reads. So it's like you traverse on the graph, and these are the random walks. And in our business, we found that usually when we try to match some complex patterns with a longer temporal window, and you get more outputs, and you want to take more the vertex check and which is the simple read here for the outputs of the complex read. So here we at the formula here is time-biased random walk, which means the longer temporal window in the complex read queries, it will indicate some more the simple read queries following it. And in this paper, we also conduct two experiments to demonstrate the choke point analysis. The first experiment is on the temporal queries. This is actually the layout of the 2GraphDB storage. We store in the vertex and edges. We use a linked list, and the key here is the vertex, and the value here is the edge list. If we sort the edges by the time steps, and we can achieve around 40 speed up on the TCL1 with the temporal storage. And the second experiment here is we push down the pass level predicates to the expanding operators in the 2GraphDB. You can see the right filters here, which is we defined we want to match this path in ascending order of the temporal order. So we push down these kind of filters to the volume expand operators, and you can achieve at least 70 speed up on the queries with recursive path filtering. And here's the takeaways and our future work. We profiled the financial graphs and found features including the temp step properties and the agent multiplicities and the unbounded skewness. And we provide scalable, but currently we only supported scale factor 100 because we have some performance problems in the data generator, which we will solve it in the future plan. And the data generator is also configurable, and it conforms to the data features to simulate the financial graphs. And we identified several choke points embedded in the financial queries and designed a transaction workload with 4 query categories. And we provide a benchmark driver and several reference implementations for the demonstration and the validation. And we conduct some choke point analysis experiments for the future system of transformations. And the plan here is the next step is to solve the performance problems in the data generated. We can support the larger data scales generation and data set generation, and we can then move to the new workload for the OLAP. It's like the SMBBI workload in the financial scenarios. We have identified some queries and choke points in our scenarios G-Flow, which is our system designed for ALAP graph computing in financial systems. Yeah, that's all I have for this financial benchmark. Thank you.